In Chapter 8, we are going to discuss gases and their properties, talk about pressure, and then finish off with the gas laws and their equations and the mixtures of gases. First of all, once again, we just got done talking about liquids and solids and whatnot in Chapter 7. But even a little bit about gases. So these are substances whose molecules are far apart from each other. They're not really next to each other. They're separated by very large distances, and those particles are moving quite fast. So they have high kinetic energies and low intermolecular forces because those interactions between the particles are very small because they're so far apart as compared to the liquid or the solid. Just a few elements out of the whole plethora of them in the periodic table exist as gases at room temperature. And in this schematic here of the periodic table, the blue, so whatever is in light blue, at least that's what it appears to me, are those elements that exist as gases at room temperature. Okay. These, all of these, the noble gases, so helium, neon, argon, krypton, xenon, radon, these gases are isolated atoms, but the others exist as diatomic molecules, so H2 and 2O2, F2Cl2, etc. But these, the noble gas column, those gases exist as just single atoms, not diatomic molecules. The low molar mass compounds exist as gases at room temperature. Now, those typically will have, as learning from the previous chapters, learning about intermolecular forces and how they affect the condensed phases, we would then deduce that these molecular compounds that have low molar masses and have very weak intermolecular forces, they will exist as gases at room temperature. And here's some examples of those molecular compounds. It's not an extensive list, but here's a few examples and their names. And these exist as gases at room temperature, and they have low molar masses as well. Now, gases are composed of molecules that are separated by large distances as compared to the size of the particles. But gases can be compressible because a lot of what's in between here, between these particles, is just empty space. I can compress it. So I can put a piston up here, and if I push down on it, that gas can be compressed. And we are very familiar with that because all of us have used a syringe at some point in time where we've depressed the plunger and we've condensed the air that's inside that syringe. So this is the first stipulation of the kinetic molecular theory of gases. That it's very simplified here for the purposes of this course, but we use the kinetic molecular theory of gases to explain gas behavior, the behavior of all these gaseous molecules. So first of all, they're separated by relatively large distances and they can be compressible. Now, they also move randomly and they're constantly moving. They collide with each other and the walls of the container without any energy being lost during those collisions. We call them elastic collisions. They don't lose energy as they collide with each other or with the walls of the container. The higher or the more frequent the collisions are, the higher the pressure is of the gas. If you think of the number of collisions per unit area, that would be the pressure. So the force comes from these molecules hitting the container, and that force per unit area gives me the pressure. The more gas molecules I have, the higher the pressure is going to be, because I'm going to have more collisions per unit area than if I have, right, a gas molecules that are not as dense, or that they're much further apart. So you can see here where the gas is not compressed, the pressure is right here. But as I compress the gas, the pressure increases because now my area is getting smaller. So I have more collisions per unit area if I condense the molecules of gas. Gas molecules do not exhibit strong intermolecular forces, either attractive or repulsive. They just don't interact with each other. Really, it's negligible because they are so far apart from each other. The average kinetic energy of the gas molecules is proportional to the temperature of that sample. And you can see, if I'm just looking at nitrogen gas, for example, and here's, I plot the number of molecules versus the speed of the molecules, which translates really to the kinetic energy that they have and the temperature, right? So here's the temperature. At 100 degrees, most of them have a speed of about, give or take, 250 meters per second. But if I increase the temperature from 100 Kelvin to 300 Kelvin, you can see that they're shifting towards higher molecular speeds. So now the higher, right, the molecules that, the number of molecules that have kind of the average molecular speed here would be around 400. And if I increase the temperature even more to 700 degrees, the average speed then becomes about 650 or so. So you can see that as I increase the temperature, the molecules increase the molecular speed or their kinetic energy. What is pressure? Pressure is exerted by gases on what they are touching, right? So if a gas is in a container, they touch the walls of that container, and so the pressure is felt by the container's walls because the gas molecules are hitting that container. Atmospheric pressure, we sort of mentioned this earlier, is the pressure that the atmosphere of the Earth exerts on us, right? So we have a column of air above us, right? And the air gets to thin as it goes, the higher above the Earth we go, but the column of air above us exerts a certain pressure. And that's where we get the atmospheric pressure. So here's an example of that, right? So this is, if we remove the air in this container, right now there's gas in there. It could be just air, but there is some sort of a gas that is inside this container, and it's balancing the pressure from the outside. So the pressure inside the container is the same as the pressure on the outside. Now, if I hook up a vacuum pump to this container and I remove the air, look at what happens. It actually crushes, right? So it crushes inward. Why? Because the pressure of the gas outside is now greater than what's inside, and so it crushes it. You can see that sometimes in a milk container, right, that gets distorted. It gets kind of sucked in. That's because somehow the pressure on the outside became higher than the pressure on the inside. But if you open the cap of the milk and whatever is inside, right, it's got some gas inside, some air. If you open up, air is going to rush in and make the pressure inside the milk jug the same as the pressure outside, and the shape of the container is going to go back. So we have been observing this, but we haven't necessarily thought in terms of pressure of a gas. The pressure is really a force because the gas molecules they collide with the surface of a container, and therefore they exert a force on that surface. And here is what pressure is defined as then. The pressure is the force that is exerted by the gas molecules per unit area. Now, you can see, we talked about this, that if I compress the gas in that cylinder, I reduce the area. So if I make this smaller, and I don't change the force, but I make the area smaller, what is going to happen to pressure is going to increase because the force doesn't change, but this number gets smaller. So if I divide a number by a smaller number, the pressure is going to increase. So the second cylinder has greater pressure than the first cylinder because it has a smaller area. We measure pressure in different units. Actually, there's several different units that we measure. In the English system is measured as pounds per square inch, PSI. And these are the values of air pressure at sea level. We can measure it in pascals after the scientists who did some work with pressure and with gases. And here's the value for that. Kilopascals is the same, it's just for ease of writing, instead of writing 101,325, we just do 101.3. Typically, we don't even write the last two digits here, kilopascals. In atmospheres, 1 atmosphere. Inches of mercury, millimeters of mercury. So 29.92 inches of mercury, 760 millimeters of mercury, 760 torr, or in bar, so 1.01325 bars. These are all units that are used, and they are interchangeable. So I can just say 1 atmosphere is equal to 14.7 psi, pounds per square inch. 1 atmosphere is equal to 101.325 kilopascals. 1 atmosphere is equal to 760 millimeters of mercury, or 760 torr, etc., etc. Or I can say 760 torr is equal to 1.01325 bars, and so on and so forth. Here's a sample problem for you to try. So perform the following pressure conversions. 695 millimeters of mercury, convert them to units of atmosphere. Knowing that 1 atmosphere has 760 torr from the table previously, just like I showed you how to relate one unit to another. Convert 3.45 atmosphere to psi and 2.87 bars to units of torr. How do we measure pressure? Well, here's the barometer. Now we don't think about it. We just go to weather.com or whatever website that you prefer to use, and they give us the atmospheric or the pressure, depending on if we have a cold front or a warm front moving in or whatever. But somebody has to measure the pressure, and we use several different ways, but one of them that is more common is a barometer. We use a barometer. What happens? How do we measure that? We take a long glass tube that is closed at one end. See how it's closed here? We fill this up with mercury. I mean, now we don't do it with mercury, but this is really how it was done before then. We fill it up with mercury, and then we invert it carefully into a container that is full of mercury. So mercury inverted into mercury. Now, what's going to happen is that some of that mercury is going to flow out from the tube on the outside. When that tube doesn't flow anymore, if we measure from the surface of the mercury on the container up to the highest level of mercury in that glass tube, that's going to give us what the atmospheric pressure is, because that's what's keeping the mercury, the rest of the mercury inside this glass tube, is the pressure that the atmosphere exerts on this liquid, that it doesn't allow for the rest of this column to come out into the reservoir. This is how we measure atmospheric pressure, by using a barometer.